Hi everyone, welcome back to EE Education, your go-to place for mastering electrical engineering concepts. In today's video, we will dive into the transient response of DC and AC networks. Whether you are a student or a professional, understanding transients is crucial for analyzing how circuits behave over time. So let's get started. Our introduction to transient response. First, let's talk about what transient response means. When we switch a circuit on or off, or when there's a sudden change in circuit's operation, the voltages and currents don't change instantaneously. Instead, they transition from one steady state to another. This period is what we call the transient response. Here we can see the circuit switching on or off. Our section 2 is transient response in DC circuits. Let's start with DC circuits. We will focus on two key components, resistors and capacitors RC circuit and resistors and inductance RL circuits. In an RC circuit, the transient response occurs when a capacitor charges or discharges through a resistor. Let's look at the charging process first. When a DC voltage V is applied to an RC circuit, the voltage across the capacitor, that is Vc of t, changes according to this formula. Vc of t equals to V into in bracket 1 minus e to the power minus t upon RC. Here R is resistance, C is capacitance and T is time. As we can see from the graph, the voltage across the capacitor gradually increases and approaches the supply voltage over time. Now let's consider the discharging process. When the capacitor discharges through the resistor, the voltage across the capacitor is given by Vc of t is equals to V0 into e to the power minus t upon Rc, where V0 is the initial voltage. We can see in this case the voltage decreases exponentially until it reaches 0. Next, let's look at the RL circuits. Here the transient response happens when an inductor builds or collapses its magnetic field. For the current through an inductor I of t, when a DC voltage V is applied, the formula is I of t is equals to V upon R into 1 minus e to the power minus RT upon L, where R is resistance, L is the inductance and T is the time. We can see the graph current versus time for building magnetic field. The current starts from 0 and gradually increases to V upon R, the steady state current. Similarly, during the collapsing of the magnetic field, the current decreases exponentially. I of t is equals to I0 e to the power minus RT upon L, where I0 is the initial current. We can see the graph current versus time for collapsing magnetic field. Now let's move on to the AC circuits. Here we will focus on RLC circuits, which includes resistors, inductors and capacitors. So the section is RLC circuit. We can see series RLC circuit. In series RLC circuit, the transient response is more complex due to the interplay between the resistor, inductor and capacitor. The voltage and current can oscillate before reaching a steady state. We can see the diagram of series RLC circuit. The general form of the voltage across the capacitor or inductor is given by V of t is equals to A e to the power minus alpha t cos of omega dt plus phi, where alpha is the damping factor, omega d is the damped natural frequency, A is the amplitude and phi is the phase angle. We can see the graph of damped oscillations. There are three possible scenarios for the transient response in an RLC circuit. First is overdamped, no oscillation, the system slowly returns to equilibrium. Second is critically damped, no oscillation, the system returns to equilibrium as quickly as possible. Number 3 is underdamped, the system oscillates before settling down. Let's briefly look at the each case. We can see the diagram of overdamped, critically damped and underdamped responses. Now let's apply what we have learned with a practical example. Consider a simple RC circuit with a resistor of 1 kilo ohm and a capacitor of 1 microfarad connected to a 10-volt DC source. When the circuit is switched on, the voltage across the capacitor follows Vc of t is equals to 10 into bracket 1 minus e to the power minus t upon 1 kilo ohm into 1 microfarad. After solving, we get Vc of t is equals to 10 into bracket 1 minus e to the power minus t upon 0.001. As you can see, the voltage across the capacitor rises to 10 volt following the exponential curve. So to summarize, we have covered the transient response of DC and AC circuits, focusing on RC, RL and RLC circuits. We have seen how resistors, capacitors and inductors behave during the transition period when the circuit conditions change. Understanding these concepts is crucial for designing and analyzing circuits in both academic and practical applications. Thank you for watching. If you found this video helpful, please give it a thumbs up and subscribe to EE Education. For more educational content, don't forget to hit the bell icon to get notified about our latest videos. If you have any questions or topics you would like us to cover, leave us a comment below. See you next time. Happy learning.